Welcome to the end of your 8-video week of mathematics. And most people are probably, hopefully, watching this video because you probably don't know what the intermediate value theorem is. Okay, so let's talk about it. One of the important things when talking about polynomial are we say they're continuous and smooth. Okay, so when I say continuous, I mean it doesn't have gaps, right? So polynomials can't look like this. They're connected everywhere. This is not what polynomials do. Polynomials, these are really nice. They're connected. When I say they're smooth, that means this is like an absolute value function. This is not smooth. This is very jagged, right? Smooth would be something like this. Okay, there are precise mathematical definitions for these concepts, but this is the general idea of what it means to be continuous and smooth. This is not smooth. This is not continuous. This is smooth. This is continuous. And polynomials are this bottom case, right? And that gives us an advantage because something that we do from time to time is we want to look about zeros. Okay? If I tell you a polynomial is up here at this point and down here at this point, I don't know necessarily what happens between these points. But since polynomials are continuous, right, maybe they connect like that. Or who knows? Maybe they connect like that. Doesn't matter what's going on, but somehow, right? Somehow these 2 points have to connect. And I don't know what it's going to look like, but they have to connect. So what the intermediate value theorem says is if we have a situation like this, we have to cross the x-axis at least one spot between those 2 points. So here again, we crossed. Here we crossed 3 times, and here we crossed. If you connect, there's no way to connect these points like a polynomial unless it crosses somewhere between the points. All right, so let's state the intermediate value theorem. And I hope you enjoy seeing me write this because I will never write intermediate value theorem ever again for this class. I'll always write IVT. This is a very common abbreviation for this. A lot of my abbreviations I just use for myself, but this one's super common. And it says, if f of x is a polynomial function, technically there's a more general version of this theorem, but for our class, we'll say if f of x is a polynomial function, and the signs, so positive and negative, of f of a and f of b are opposite, then there must be a zero between a and b. So if the function values have opposite signs, there has to be a zero between their x coordinates. Right here, right, this function value was positive. This one was negative. If that's a and that's b, has to be a zero between a and b. And there was right here. Or again, if this is a and this is b, there has to be at least, there must be a zero. You could say at least one. There could be multiple. Okay. We're going to use this with example 7. Example 7, use the IVT to verify there's a zero, at least one, in the interval a to b. So, part A, I'll give you a function, f of x equal to x to the 5th minus 2x between x equal to 1 and x is equal to 2. We are going to prove that we must cross the x-axis between 1 and 2 using this theorem. So how do we use the theorem? Let's see. If f of x is a polynomial function Now we got a polynomial function right here, degree 5. And the signs of f of a and f of b are opposite. We need to check this. Okay? We need to show f of a, which is 1, and f of b, which is 2, have opposite signs. If we can do this, then we win. then we can use the theorem to conclude there has to be at least a 0, 1, 0 between these two things. Let's find f of 1. And let's find f of 2 and show that they have opposite signs. We plug in 1 here, we get 1 to the 5th minus 2 times 1. 1 to the 5th is just 1. 2 times 1 is 2. All right, so it's negative over here. When x is 2, what do we get? We get 2 to the 5th minus 2 times 2. Just plug in 2 to this function. 2 to the 5th is 32. 2 times 2 is 4. This will be 28, which is positive. Great. Opposite signs. So, by the IVT, there's at least 1, 0. In the interval, 1 to 2. This is kind of a proof, so there's not really an answer. The answer is all of our work. And again, what we have right here is at 1, or at some negative. When x is 1, our function value is negative 1. When x is 2, our function value is positive 28. So somewhere in that interval, we must have crossed. That's what's going on right here. Okay. Do another one. Part B. F of x is equal to negative 2x cubed minus x between x is equal to negative 1 and x is equal to positive 1. So again, we just want to show, do these function values have opposite signs? So negative 1 and positive 1, are they opposites? Negative 1, oh my word, there's so many negatives, right? If you plug negative 1 everywhere here, be very careful. Let's do this in steps. Negative 1 cubed is still negative 1. Subtract negative 1 is a plus 1. Now negative 2 times negative 1 is positive 2. Okay, we have 3. This is a positive number. So hopefully this thing over here is negative. We can use the IVT. When x is equal to positive 1, we have 2 times 1 cubed minus 1. Negative 2 times 1 minus 1. Negative 2 minus 1, or negative 3. That's negative. So since they're opposite signs, right, opposite signs, so there's at least 1, 0. In our interval, negative 1 to 1, negative 1 to 1, by the IVT. You don't really have to box it, because again, the whole thing is our answer. It's kind of like a proof. That's the intermediate value theorem. And that's the sections. Good luck, and let me know if you have questions.